Welcome back to Gravi-cation, your platform for excellence. So this is our second video on acid, base and salt series. So in today's video, we will be looking at basicity, acidity and alkalinity of substances. First of all, we would like to dive into the concept or the idea of what basicity is. Therefore, basicity is simply the number of replaceable hydrogen ion. The number of replaceable hydrogen ion that is present in one molecule of an acid. We have hydrochloric acid, we have phosphoric acid, we have nitrous acid, and then we have acetic acid. These are four examples of acid, and each of these acids have a number of replaceable hydrogen ion. So for the first example here, which is HCl, the number of replaceable hydrogen here is 1. Therefore, HCl will be called monobasic. Now, for the phosphoric acid, the number of replaceable hydrogen here is 3. 3 replaceable hydrogen ion are present in phosphoric acid. For that reason, phosphoric acid will be called a tribasic acid. Also, in our nitrous acid, we can see that the number of replaceable hydrogen ion here is 1 to become monobasic. Now, there is a very unfamiliar situation here with acetic acid. We are having 4 hydrogen ions here, but where the acidity is focused is on this functional group here called the carboxyl group. Now, 1 hydrogen ion is present in this particular functional group, which is responsible for the acidic property of this compound. Hence, the number of replaceable hydrogen ion here is 1, meaning acetic acid is monobasic. Okay, so these are sample questions for your benefit. Please, can you look at each examples here and state the basicity for me? The basicity, yes. 1 minute I think will be enough. So the basicity of the first acid here, hydrobromic acid, is 1, which is monobasic. That of sulfuric acid is 2. That's dibasic. That of nitric acid is 1, monobasic. That of carbonic acid is 2, dibasic. And that of hydrocyanic acid is 1. These are basically the basicity of the acids that are written down. Now, we will now move to the other concept, which is acidity. Acidity is simply the measure of strength of an acid. The measure of strength of an acid, that is how strong or weak an acid is. We can also define it as a substance ability to produce hydrogen ion when dissolved in water. Alkalinity. Alkalinity is the measure of the strength of a base. The measure of the strength of a base. It can also be defined as the ability of a substance to produce hydroxide ion when dissolved in water. We have a third definition of alkalinity, which is the ability of a substance to neutralize an acid or resist acidification. Both acidity and alkalinity can be measured by the use of what we call a pH scale. Now, a pH scale is just a range of numbers that are used to check how strong a substance is with regard to its acidic or its alkaline content. It is measured from 0 to 14, with 0 down to 6 as strongly acidic, while 8 down to 14 alkaline. At pH 7, a substance is said to be neutral. Okay, so we'll be moving now to the next concept, which is the classes of acid and base based on their strength. The first on our list is strong acid. A strong acid is a substance that dissociates completely when dissolved in water to produce hydrogen ion. We will be looking at some of the examples of strong acid. The first on the list is hydrochloric acid, written as HCl. Second on the list is hydrobromic acid, which is written as HBr. Third, we have hydroiodic acid, HI. We have sulfuric acid, that's H2SO4. We have nitric acid, that's HNO3. And then we have perchloric acid, HClO4. The second is the weak acid. Weak acid is a substance that when dissociated or dissolved in water produces hydrogen ion when it is partially dissolved. So there's no complete ionization, or in the case of weak acid, there is partial dissociation. Examples of weak acids include, we have hydrofluoric acid, HF, we have trioxosulfate 4 acid, we have HClO, we have HNO2, that's nitrous acid, we have acetic acid, CH3, COOH, then we have hydrogen cyanic acid. They are all weak acid because they partially dissociate to produce hydrogen ion. Please, it is important to note that all organic acids are mostly weak acids, while oxy acids, the lesser the number of oxygen, the weaker acids they become. Alright, next is the strong base. So strong base are substances that completely dissociate or dissolve in water to produce hydroxide ion as the only negative ion. We have some examples as, we have potassium hydroxide, that's KOH, sodium hydroxide, NaOH, barium hydroxide, cesium hydroxide, rubidium hydroxide, calcium hydroxide, and calcium oxide, otherwise called quicklime. Finally, on the classes of acid and base is the weak base. Are substances that dissociate or ionize in water to partially to produce hydroxide ion. Few examples include, so we have ammonia, we have aluminium hydroxide, lead hydroxide, iron 2 hydroxide, copper 2 hydroxide, zinc hydroxide, and ammonium hydroxide. Please, a take home from this is that what most hydroxides of elements with higher oxidation number are mostly weak bases. You can equally say most hydroxide of transition metals are what? Weak bases. So we'll be moving straight to the next aspect of the video, which is basically pH calculation. Before we look deep into some questions from this section, there are certain formulas that are of very big importance to you navigating your ways through pH calculation. Few of these formulas are written below. So the first formula to remember here is that what? pH is equal to the log of the inverse of your hydrogen ion concentration. It can equally be written as negative log of your hydrogen ion concentration. Now, the other formula, which is formula number 2, says that negative log of the hydroxide ion is equal to your POH. So POH is equal to log of 1 all over the hydroxide ion concentration, or negative log of the hydroxide ion concentration. There's a relationship between the pH and pOH, which is pH plus pOH equal to 14, while the relationship between your concentrations of your hydrogen ion and the hydroxide ion is given as 1 times 10 raised to the power of minus 14. We will be moving straight to answering some certain questions in this session. So our first question from this section is this. The question is, what is the concentration of the hydrogen ion in moles per Dn cube of solution of pH 4.398? This is our solution. So the question is to look for the hydrogen ion concentration, and pH was given to us. So we're using the first formula, which is pH equal to log of 1 all over the hydrogen ion concentration. Therefore, our pH was given to us as 4.398, which is equal to log of 1 all over the hydrogen ion concentration. Now, we need to take the antilog of our pH, which is written as 10 raised to the power of 4.398, which is now going to be equal to our 1 all over our hydrogen ion. So by checking out for the calculation, we have 25,003 approximately. 25,003 approximately, which is equal to 1 all over our hydrogen ion. Now the question asks for the hydrogen ion concentration, so we need to take the inverse. We can make this over 1. Therefore, our hydrogen ion concentration will be equal to 1 all over 25,003, which invariably will be 0.000399, which will approximately be 4 times 10 exponential negative 4 times 10 exponential negative 5. 4 times 10 exponential negative 5. So we'll be taking another question. Sample 2. A sample of orange juice is found to have a pH of 3.8. What is the concentration of the hydroxide ion in the juice? Now, please, it is important to know that orange juice is acidic due to the presence of citric acid. Therefore, we have been given the pH and we are asked to calculate the concentration of hydroxide ion, which is associated to the pOH. So it is important to first get the pOH. So in this question, we will be using the formula that relates the pOH and the pH, which is written as this: pH plus pOH equal to 14. So we're giving our pH as 3.8. We are to look for the pOH first. Therefore, we'll be having the pOH as 14 minus 3.8, which would be giving us 10.2. So our pOH is 10.2. Now we can move further to calculate our hydroxide ion concentration by using the formula pOH equal to log of 1 all over our hydroxide ion concentration. We'll be having 10.2 equal to log of 1 all over our hydroxide ion. So take the anti-log, so we're going to have 10 raised to the power of 10.2 equal to 1 all over the hydroxide ion. Alright, so we will be taking the inverse of the expression right now. So we are going to be having the hydroxide ion concentration is equal to 1 all over 10 raised to the power of 10.2, which will be giving us 6.3 times 10 exponential negative 11, which is option B. So I'll be leaving you with 3 more questions to be able to get feedback from you on the calculations of pH. So I have question 3 here that says you should calculate the pH of a solution of 0.0001 mole per dm cube HCl. Also, question 2 says what is the pH of 0.001 mole per dm cube sodium hydroxide, while the last question says ion concentration of the solution of sodium hydroxide of pH this is what. So please leave your answer in the comment section. Thank you for such a beautiful session. See you in the next class.